In the last video, we have seen what is periodic motion, what is simple harmonic motion, what is the difference between the periodic motion and simple harmonic motion, and when to use the word oscillation and when to use the word vibration. Okay, these ideas we have seen in last class. And today we are going to see another quantity, simple harmonic oscillator. In short, we can address as SHO. What it is, the body which performs simple harmonic motion is known as simple harmonic oscillator. Quite obvious. Okay, so for the simple harmonic oscillator, we define different physical quantities. The first quantity what we define is known as displacement. But to understand this, we will take this example. I have taken an example here. This diagram already familiar in chapter 6, work, energy and power. We have seen this diagram. So there's a horizontal elastic spring, and one end is fixed with a fixed support. In other end we have a body attached, initially body at rest, so resultant force equal to 0, and that body is made to move on a horizontal surface which is frictionless. Because I told you in the beginning we studied simple harmonic motion under ideal case, that means no resistive force. That's why we have to take a surface as a frictionless surface. Okay, and initially the initial portion of the body we take as a 0, x equals 0, and that is a fixed point. About each other body going to oscillate. You slightly pull and lean, body is going to oscillate like this. Okay, so this is going to move on a straight path, repeated motion. That is going to be a simple harmonic motion. So about which point it is making oscillation, that fixed point we are going to call as a mean position. Then that fixed point we are going to call as a mean position. So from this we will go for the definition. First one, what it is, displacement, distance of SHO from mean position. That means from a mean position, how far simple harmonic oscillator moves, that is called as a displacement. It is not the simply change in the position, so it's how far it is away from the mean position. Okay, so but by using this displacement, we cannot know the direction of motion of simple harmonic oscillator. I'll give an example. Say from x equal to 0 it goes to one particular place x. What the displacement? X. Okay, it goes further, it takes maximally for displacement and comes back to the same point. Okay, now how it is moving? Now it is moving towards the mean portion. Previously it was moving away from the mean portion, now it is moving towards the mean portion. But what the displacement? Same value x. So that's why by knowing what is the value for displacement, we cannot know what is the direction of motion of simple harmonic oscillator. Then how to know the direction of motion of simple harmonic oscillator? There are two ways. One method is by using velocity. Velocity will always show the direction of motion. Okay, so that's why using velocity of simple harmonic oscillator, we can find what's the direction of motion. Okay, one thing. And there is one more quantity we are going to define. So by this also we can find what's the direction of motion of simple harmonic oscillator. Okay, so that's about the displacement. And when it oscillates on either side, it takes maximum displacement, and that is called as amplitude. Amplitude, maximum displacement of simple harmonic oscillator from the mean portion. Okay, now in the diagram, towards right, actually if x equals 0, towards right we take positive x-axis, this side we negative x-axis. That's why this side towards right x is taken as a positive, towards left x is taken as a negative. Same amplitude also, and towards right taken as a positive and this side is taken as a negative. So that's why when the body oscillates between 2 points. One is plus a, other is minus a. That's the total length of the path on which oscillating is what? 2a. When the body makes one oscillation, what's meaning one oscillation? Starting from say x equals 0, goes to plus a, come back to 0, goes to minus a, come back to 0. That is one oscillation. So what the total distance traveled? 4a. What the total displacement? 0. Again, I can come back to the same place. There's a resultant displacement equal to 0. Okay, but total distance traveled for one oscillation equal to 4a. Okay, so that's about the displacement. So that's why by knowing displacement, we cannot know what's the direction of motion of simple harmonic oscillator. Okay, next quantity, period. Actually, what the simple harmonic motion, a type of periodic motion. It's in the repeats regular interval. So what the minimum time it needs to repeat the motion? The time interval we call as a period. There's a period we can define least time taken to repeat the motion. Okay, so it's the least time taken to repeat the motion. That's called as a period. Or we can say it's the time taken to complete one oscillation. Yeah, to make one oscillation, what the time it takes. That's called as period. Period, you know, it measure in terms of a second. Next quantity, what we define? Frequency. Frequency we denote as a nu. The symbol already you have seen. So this is symbol what we use. What is frequency? Number of oscillations made in 1 second. Okay, that's suppose you know the total number of oscillation and total time you taken, then total number of oscillation per time will give what's the value for the frequency. Okay, that's the definition goes like this: number of oscillation made in 1 second by the simple harmonic oscillator, or we can write number of oscillation upon total time. So that's why from this we can get the formula for frequency. Okay, or we can say we can get relation between the frequency and period. What it is, to make one oscillation, what the time taken? Period. So that's why frequency we can write 1 upon t. So that's why unit comes second per minus 1, and there are other quantities also got a unit second per minus 1. Actually, when you study viscosity, we have seen velocity gradient. Velocity gradient also got a unit second per minus 1, but there we call second per minus 1 only. Whereas here, second per minus 1, when you talk about frequency, is denoted as hertz. It is named as hertz. Hertz is the name of scientist. That's a full name you write in a small letter. But when you give a symbol, you have to give first letter as a capital letter. So that's the symbol what you have to follow. And the next quantity, what we have, angular frequency. Angular frequency, we don't have any definition. The formula itself is a definition. Like a certain quantity, the formula only we call as a definition. For example, linear momentum, P vector equal to mv vector. Suppose he asked to define linear moment. How we define? It's a product of mass and velocity of particle. The same formula you say in words. Same way, this quantity 2 pi by t is known as the angular frequency. Actually, we got 2 pi nu. 1 upon t equal to frequency. Just now we got the formula. That's a 2 pi nu or 2 pi upon t. That quantity known as the angular frequency of simple harmonic oscillator. But how it is angular frequency, all this thing we'll see little later. For time we take this formula. So that's a quantity 2 pi by t is known as the angular frequency of simple harmonic oscillator. What the unit will get? Actually 2 pi is angle. So angle we measure in terms of radian, time second. That's the angular frequency got unit as radian per second. In chapter 7, angular speed, angular velocity, angular speed is scalar quantity, angular velocity vector quantity. Both they have a unit radian per second. Now we got one more quantity, angular frequency. So that also got a unit as a radian per second. So these are some of the physical quantities what we need to explain the motion of simple harmonic oscillator.